All right, so this is going to be the last screencast for our kind of early and modern atomic theory unit. And the title of this is going to be valence electrons as well as periodic trends. So valence electrons and periodic trends are what we're going to cover. The essential question for this is, there's actually two of them. How are the number of valence electrons and oxidation numbers for elements calculated? And what are the four periodic trends, and how can their effects be predicted using the periodic table? So we're just going to go ahead and get started talking about valence electrons and the octet rule. This should not be something new to you, but you're going to now relate this to electron configuration. So we're going to take what you already know and build on it a little bit. So what is a valence electron? It's the outermost electrons in an atom. So what we mean by that is it's not all of the outermost electrons. It's only specific outermost electrons, specifically the s and the p orbital outermost electrons. So what's special about them is these are the electrons that are involved in bonding. Why are the noble gases extremely stable? They're considered inert, and they don't readily bond to other elements because they have 8 valence electrons. So that's where the octet rule comes in, with 8 valence electrons. So we're just going to be looking at the outermost s and p electrons. So in the outermost energy level, the ones that are the furthest out, and only the s's and the p's. So the octet rule, elements usually react in such a way as to attain the electron configuration of the noble gas closest to them in the periodic table. They want to be like a noble gas. Everything wants to be full. All noble gases have their full outermost s and p. So they have 2 of the s electrons and 6 of the p electrons in their row. So elements that tend to be on the right side of the table, if they're already pretty close, then they just move forward to the next noble gas. A good rule of thumb is if they have more than 4 valence electrons, it's going to be easier for them to gain. If they have less than 4 valence electrons, it's going to be easier for them to lose. So elements on the left side are going to move back to the noble gas of the previous row. And we're going to label all of this on your periodic table, so you'll be able to predict what's going to happen in each column. Atoms will gain, lose, or share electrons in chemical reactions to attain this more stable energy state, to get to 8. That's their point. So any of the chemical reactions that we're going to do in our next couple of units, when we start looking at bonding and ionic and covalent bonding and nomenclature, we're going to start naming compounds. When we do this, you're going to come back to this valence electrons all the time and the octet rule. Well, what is it going to do to try to get to 8? Is it going to gain or lose, and how many will it gain or lose? So when we talk about it gaining or losing, that's what we mean by forming an ion. So it's going to gain or lose electrons to become more stable. I know that seems weird, that you would think that having a charge would make it more stable. But in terms of the number of electrons in its outermost shell, when we look at a Bohr model, it wants to try to have a full outermost shell, regardless of what charge it then has. So ions are electrically charged particles that result from a gain or loss of 1 or more electrons by the parent atom. So that atom is going to lose or gain electrons to become more stable. So a cation is positively charged, so that's what we call a positive ion. All of the metals are cations. So if you think about this, all of the metals are then going to go through the process of losing electrons. All metals want to lose, and they form positive ions. So for example, sodium loses 1 electron and forms the sodium ion. Anions are negatively charged ions. And they result from the gain of electrons. So an example is fluorine. Fluorine is going to gain 1 electron and become fluorine with a 1- charge. So all of our metals are cations, and all of our nonmetals are anions. So ion formation and the octet rule. All atoms of a group lose the same number of electrons. This is what makes the periodic table so awesome. Everything in the same column behaves the same way. So everything in column 1 has 1 valence electron, and it all wants to lose that 1 valence electron. So it's going to result in an oxidation number of 1+. Everything in column 2 wants to lose those 2 valence electrons, and it forms a 2+ ion. So here it's showing you aluminum. Aluminum If you look at the noble gas configuration for it, if you just look at its electron configuration, it has 3s2, 3p1. So right now it has 3 valence electrons, and it's in the third column for the representative elements. So that makes sense. It has 3 valence electrons. Well, what it wants to do, it's easier at that point for it to lose 3 than it is to gain 5. So it loses those 3 electrons and it becomes aluminum 3+. Now, it looks like neon in terms of its electrons. It doesn't become neon because remember, it's not losing any protons. So it just looks like neon in terms of its electrons. So that's forming a cation. Here's another example with cation formation. Whoops. The metallic elements tend to form positively charged ions. So sodium, for example, and everything in column 1 has 1 valence electron, and it will lose that 1 valence electron. And when it does, everything in column 1 forms a 1+ charge. That's its oxidation number. Anions, so everything basically after column 4, so from the nitrogen group on over, all of these want to gain electrons. It's easier for them to gain to get to 8 than it is for them to lose. So non-metallic elements tend to form negatively charged ions called anions. So if you look at this right here, oxygen has 6 valence electrons right now, so 2s2 and 2p4. So it's much easier for it to gain 2 electrons than it is for it to lose these 6. So it gains 2 electrons to be now full like neon, but it's still oxygen. It's just oxygen with a 2- charge. So using this octet rule, we can draw Lewis dot structures. So the octet rule is very helpful in predicting the charges of ions in the representative elements. Transition metals, the ones in the middle, we're going to kind of ignore those for right now. We're going to pretend those don't exist when we're talking about valence electrons because they tend to form multiple stable atoms or stable ions. You're going to learn about those transition metals and intertransition metals when we do our nomenclature and our naming unit. But for right now, we're just going to stick with the representative elements, meaning the main group elements that we know their charges. Whereas the transition metals, we're just going to pretend that they don't exist right now. So examples using the octet rule. Give the charge of the most probable ion resulting from these elements. If you don't know how to do this by their column number, we're going to go through this and review it in class. And then we're going to go through and determine the isoelectronic pairs as well. So isoelectronic just means they have the same number of electrons. So when you look at it, when you go through and figure out how many electrons chlorine with a 1- has and how many electrons argon has, we're going to see if they're isoelectronic to each other. So you can go ahead and you can figure that up if you know how to do it. If not, just write these down in your notes and we will complete them in class's review. So calculating subatomic particles and ions, you should be able at this point to tell me how many protons, neutrons, and electrons are given in each one of these. And we know these are ions because it's got charges on there. So the mass number is protons plus neutrons. The bottom number is the number of protons. And then you can use that to figure out the number of the number of electrons. So you should be able to complete this at this point. And we'll go over these 3 if we need to during class. Okay, so the last section of this are going to be the trends in the periodic table. When we look at the periodic table, there are just some basic patterns that we might see, like what happens as we go left to right, or what happens as we go from top to bottom. So there are 4 basic patterns or 4 trends that we see in the periodic table. Atomic size, ion size, ionization energy, and electron affinity. So we're going to talk about each one of those. So atomic size, this is what happens as you go left to right and top to bottom. You will see as I go left to right, the atoms get smaller. So as I'm going left to right in a row, in a period, the atoms generally get smaller. Not always, there's a few exceptions in there, but for the most part, the trend is for them to get smaller as I go from left to right. And then you can see what is the trend as you go from top to bottom. They get bigger as I go down. So they get bigger as I go down, and they get smaller as I go across. So fluorine's the smallest, and cesium and francium are going to be the biggest. Well, why does that happen? The reason it happens is as I go down, I'm adding a new energy level, a new quantum level. Every single time I go down, I'm going from, column number 2 or row 2 to row 3 to row 4. So I'm getting bigger. The reason they get smaller is all I'm doing as I go across is I'm filling in these orbitals that I have. I'm not adding any new orbitals, at least that are a further distance from the nucleus. They're all the same distance, but I am increasing protons. And if you guys remember, protons are about 2,000 times bigger than an electron. So as I increase the protons, I get more control. There's more control holding those electrons in place. Okay, so for cations are smaller than their parent atom. They have more protons than electrons. So again, you have an increased nuclear charge. You have more of the protons to make it smaller. You have extra protons, they're going to pull those remaining electrons closer into the nucleus. So the same reason why the atoms get smaller as you go across. If I increase the number of protons, they just are going to get smaller. Anions tend to be larger. They're going to have more electrons than protons. And that's because the excess negative charge reduces the pull of the nucleus on each individual electron. So as I tend to add electrons, or I just have the regular size atom and I increase the number of electrons with it, I don't change the number of protons, they're going to get a little bit bigger. So that's just a little bit about cation and anion size, which we will draw ion size on your periodic table. So what we're going to do in class is I'll just draw a periodic table on the board and we'll just go through all of the different trends. So ionization energy is our third trend. That's the energy required to remove an electron. So if I just have an isolated atom, how hard am I going to have to work to remove an electron from it? Like if I want to go up and I want to steal an electron. If it has a low ionization energy, I'm not going to have to work very hard. I'm not going to have to put up a fight, or it's not going to put up a fight. It's actually going to be more than happy for me to take that electron. Think about the metals. Metals want to lose those valence electrons, so they're going to be more than happy to get rid of them. So they have a low ionization energy. The nonmetals, however, want to gain electrons. So you are going to have to put up a huge fight if you want to try to steal an electron from something that wants to gain electrons. So for the trend for ionization energy, as you go across a period, it gets higher because they want to gain. And then as you go down, it actually goes down, ionization energy goes down, because they get weaker. They're just too big to control the ones on the outside, and so it's easier to steal electrons from those outer layers. Electron affinity is the energy released when a single electron is added to an isolated atom. So if I were to just give the atom an electron, the electron affinity gives you or tells you how easy it is for it to take it. So when you think about ionization energy versus electron affinity, they're exact opposites of each other. How much do you want it versus how much do you not want it? Ionization energy is you wanting to lose it. Electron affinity is you wanting to gain it. So the nonmetals are they have more electron affinity. They have a higher electron affinity than the metals do. So nonmetals, so as I go across the periodic table towards the nonmetals, it goes up. And then as I go down, it also goes down because they just get too big to really care. So we are going to draw all three of these periodic trends on your periodic table, and we will do some examples. So I know in your notes it tells you, what happens as you move from left to right. In a period, what happens as you move from top to bottom in a column. I have verbalized that for you. I didn't necessarily put that. That's not in the actual notes, the presentation notes, but we will go through those kind of briefly in class. We are also going to cover electronegativity, which is not part of your slideshow. Electronegativity deals with how desperate are you for electrons when you are in a bond. So making the polar and nonpolar bonds, you should have heard of those terms before. That's because of electronegativity. So when we label our periodic table, we will go over the trends briefly and we'll cover electronegativity in class.